the Peru-Chile subduction zone, looking back after the 2015 Illapel earthquake.
Hey, thanks. This is a nice full house. Today I'm going to talk to you about seismic processes at the Peru-Chile subduction zone. This is motivated by a series of great earthquakes recently, and especially last year's great Illapel earthquake. Or maybe not. Okay. So, at the Peru-Chile subduction zone, the oceanic Nazca Plate descends underneath South America. And this is a good place to study seismic processes because it's relatively uniform along its 2,000-kilometer length. You can see the plate velocities don't vary much along strike, and the age of the subducting oceanic plate is confined to within a relatively narrow range of 35 to 45 million years. This subduction zone has hosted a lot of seismicity in recorded history. Since 1900, there have been about 1,000 magnitude 6 events recorded in this subduction zone, including the largest earthquake ever recorded, magnitude 9.5 in 1960, that occurred just to the south of this map. More recently, there have been 3 great earthquakes in the last 6 years. In 2010, magnitude 8.8 earthquake occurred offshore of the Maule region in the south. In 2014, a magnitude 8.2 earthquake occurred near the Peru-Chile border. And just last year, a magnitude 8.3 earthquake occurred in between these 2 events. And so, these prompt the question, what have we learned about seismic processes from these events? So on the one hand, they do exhibit some variability. They have different magnitudes, they generate different size tsunamis. Some of them showed precursory deformation or seismicity before they ruptured, while others had no deformation prior to the rupture. I'm going to argue in this talk, though, that these events are reflecting the same underlying seismogenic processes and physical properties of the subduction zone. So as I said earlier, this is motivated by last September's great Illapel earthquake, which experienced significant damage from both strong shaking and a tsunami. And the type of information we want to acquire from this event in order to constrain seismic processes are details about the main shock, details about the aftershock, and if there are any aseismic processes occurring. We can use a variety of observations to constrain these. So from the Illapel earthquake, we have information from GPS. So these are displacements measured at these GPS stations from the earthquake, and we see this station move about 1.5 meters to the west because of the earthquake. We have information from satellite imagery, so this radar interferogram. These fringes, each of them represents 3 centimeters of deformation, and you can count them up to see how the surface moved. The tsunami from the event also tells us about the deformation during the earthquake. You have to have shallow deformation and move the ocean floor in order to generate a tsunami that was over 4 meters high across 250 kilometers of coastline. But in this talk, I'm going to focus on what we can tell from seismic data, which includes these details about the main shock and the aftershocks. Let's start with the main shock. So in order to determine the evolution of the rupture over space and time, we divide the large subduction fault into many smaller subfaults, each of which acts as its own individual earthquake. By fitting teleseismic waveforms, we can constrain the timing and slip of each of these subfaults. So on the left here are some representative waveform fits for the finite fault model shown on the right, and you can see these are reasonably well fit. On the right, this is a view looking perpendicularly down onto the subduction fault with the trench up here at the top. This upper figure is the slip during the earthquake, and this bottom figure is the timing. So let's look a little more closely at that. The earthquake starts at the star, the hypocenter here, at a depth of 28 kilometers. We see the largest slip is about 14 or 15 meters, and this is shallower than the hypocenter near the trench. We also see this area of significant slip to the right or north of the hypocenter. From the timing, we can see that the rupture propagated both up dip and along strike. And then these yellow and red colors on the sides are after about 100 seconds. And we can see these aren't associated with much slip, except maybe this patch here. So after about 100 seconds, this earthquake was over. We could have used the other geophysical data sets I described earlier to help constrain this solution, and people have done such joint inversions. These have advantages and limitations, but generally they yield a result that's pretty similar to this one. So a first order question, given the slip distribution, is where are the aftershocks going to be with respect to the main shock slip? So to answer this question, we need good locations for these earthquakes. So we've applied a relocation technique to all of the aftershocks. And locating aftershocks offshore can be difficult, but by using multiple phase observations and running them through this algorithm, we can get better estimates of the locations and estimates of the uncertainty of these hypocenters. For example, I've shown the main shock probability distributions for the hypocenter latitude, longitude, depth, and origin time. The gray are the probability distributions from the initial location, and the red are the relocated probability distributions. So what you can see is that the main shock hypocenter moved to the south, to the west, and down via this relocation technique. So as I said, we apply this to all of the aftershocks, and we see here's the results from the relocation. This is where all of the earthquakes move. We see that in general, the earthquakes are moving to the east, but the relocation vectors are fairly small. What I want you to pay most attention to is this figure on the right. This shows the earthquakes plotted at the relocated hypocenters, and they're colored by the hypocentral depth. Now, as far as we can tell, most of these earthquakes east of the trench occurred on the plate boundary, and you can see some geographical coherence as well. There's a main central cluster of aftershocks between 15 and 50 kilometers depth. But between 0 and 15 kilometers, there's almost no aftershocks at all. We see two clusters that are somewhat separated from the central main cluster, and we see these earthquakes that are slightly west of the trench, implying they have to occur in the subducting plate. So now with these relocations, we can directly compare that with the slip distribution. So here are the two data sets superimposed, and we start to see some intriguing relationships. So the first thing you notice is that the aftershocks are outlining these areas that slipped. Then we see that there are very few, as I said earlier, there are very few shallow aftershocks, despite the fact that this is the area where we saw the highest amount of slip. And the character of slip is different in these two segments. This slip down here is patchy and heterogeneous, and the shallow slip is smooth and occurs over a broad area. Again, we see these clusters that are not associated, that are separate from the central area of aftershocks, and they're separate from the slip as well. So one way to think about these aftershocks is that they're occurring in response to stress changes generated by the main slip. To test this, we can compute the stress changes from the main shock, and that's what I've done here. So I'm not going to go into great detail into this analysis, except to say that red are areas where thrust faulting on the interface is promoted, and blue are areas where thrust faulting on the interface is inhibited. And this should make some intuitive sense to you. Where we've had slip already in these contours here, the stress has been released by the main shock slip, and so we wouldn't expect to see another earthquake there. In between the areas of slip and around and outside, we see it's red. And lo and behold, that's where most of our aftershocks are occurring. So we can do the same sort of main shock slip and aftershock comparison for the other earthquakes I described. The 2010 Maule earthquake was much larger than the Illapel event, but we see it shows many of the same characteristics. The aftershock seismicity is constrained within about a depth of 15 to 50 kilometers, and it surrounds these areas of sort of heterogeneous, deeper slip. The shallow slip here is broad and smooth and is not associated with any aftershock, and we see these aftershocks that are sort of distinct from the central cluster. Then we look at the Iquique earthquake, and again, the aftershocks don't occur in the area that actually slipped, but this earthquake didn't have any coast-seismic shallow slip. This is consistent with the tsunami observations from this earthquake. You can see it has about the same magnitude as the Illapel event, but this earthquake had a much smaller tsunami. This event was also interesting in that it was preceded by a rich foreshock sequence in the 2 weeks leading up to it, and there might have been some shallow aseismic slip in this area. So the deformation in the shallow part just happened before the main shock. So let's step back a little bit and look at the regional view again. So here is all of these finite fault models plotted on the Peru-Chile subduction zone. And we see that despite these variations that they show, they have kind of similar characteristics. They all have this seismogenic zone. This is where the earthquakes start. This is where slip is heterogeneous, and this is where most of the aftershocks are occurring. Then, those of the events that have shallow slip have smooth shallow slip and very few aftershocks very near to the trench. So a conceptual model was illustrated by Lay et al. In 2012 for a series of other large earthquakes, and we can see that this is consistent with the characteristics I've shown you. They have, I don't know if you can see that, that says seismic, which is this region in here, and they even draw these patches. And then they have aseismic up here for the shallow part near the trench, and slow tsunami earthquake. And we can match some of our observations to what they're seeing. We see the rupture is starting down here at the star. It's got patchy, deeper slip, and if the rupture is able to propagate to the shallow section, it's this smooth and broad shallow slip with sort of different characteristics than this deeper stuff. Then the aftershocks are filling in the gaps between these patches, and we sometimes see that even a little bit removed from the main area of action, there can be these aftershocks triggered far from the slip. So, to conclude, we see that the Peru-Chile subduction zone is exhibiting pretty similar characteristics along its length. There's a seismogenic zone. This is where the earthquakes nucleate and where slip is heterogeneous. We see that earthquakes don't generally start in the shallow portion, but this area can slip during big earthquakes, or it can also slip aseismically. And then we do see they show some variability, and this can depend on local heterogeneity in the subduction zone, the rheological characteristics, the stress state, or where it is in the earthquake cycle, and details of the dynamic rupture. So with that, I'll say thank you and ask if you have any questions.
Could you make a size threshold for when you get slow slip and when you get that shallow slip and when you don't? I mean, could you just say that the earthquake wasn't big enough to get up there?
Possibly. I would not personally make a size threshold for it, because I can imagine that if you had slip near that 15 or 20 kilometer depth range, but it were a magnitude, yeah, let me go back. So if we had some slip up here that was a magnitude 7 or something, that rupture could, I could imagine that rupture propagating up into the shallow part. And we've also seen some earthquakes that are slow earthquakes only, that only rupture, this shallow part. But that's maybe elsewhere in the world.
Yeah, that's different.
Does the slip in one place change the stress field in the part of the plate that hasn't slipped?
Absolutely.
So if you were to map that kind of before and after,
Yes.
and does that in itself trigger the aftershocks in those other regions, or?
Yes, that's what I think is happening.
Okay.
Chuck?
One thing you didn't mention is that outboard of where you have the high slip in the Malay and the Illapel, right? You have outer rise faulting.
Yes.
Aftershocks.
So let's look at this example. So we see these outer rise events that are occurring within the subducting.
Okay, it's not as perfect a correlation, but I see that in lots of other earthquakes. And to me, it means that maybe those seismicity regions are clues to where you can have the slow slip. Because
Yeah.
it's coupled. But you see
That's
that in
possible.
Java, you see that in Sumatra.
Yeah.
Sumatra again and again. And,
Yeah.
some of the other Tohoku
Yeah.
and the Kurils.
So I will say, if you look at some of the detailed, some of the other finite fault models, they're pretty similar to this one, but they actually put this shallower slip farther north. So that could be consistent with that.
Yeah, because if it correlated with the deeper stuff, you could say, well, it's just something propagating up. But
Right.
since it correlates with the shallow slip, it might be telling something about the shallow coupling.
Sure.
So the Maui earthquake, it looked like you had some heterogeneity in the shallow slip.
Yes, I did gloss over that a little bit. So especially up in this region here, I would agree, there is some heterogeneity there. This is a very large event though, so this slip here is probably pretty comparable to all of the up-dip slip that happened. I mean, you can look at the regional view and see that this stuff here is the same size as this stuff here. And so it's just a much larger event and will be more complicated.
On that note, we'll give Matt.
The